Good afternoon to everyone. So we are discussing a concept of filters, active filters and passive filters in the combination. So in last class we discussed about the introduction part of the filters, about pass band, stop band and all. And next we analyzed about the Butterworth filter approximation. And next we designed about various polynomials of Butterworth filter. So in today's class we're going to design a low pass Butterworth filter, first order low pass Butterworth filter. So first, before going to the design and analysis and plot response of Butterworth low pass filter, first we have to see the general requirements for designing a low pass filter first order. Okay, so in previous classes at various understanding levels we have discussed about Butterworth filter approximation, what is meant by the Butterworth filter approximation and all these things. So Butterworth filter is a simple circuit. Butterworth filter is having a simple circuit and it is having a flat response characteristic. The simple circuit is simple in circuit, but the internal circuit design is depending upon the order specification. Okay, so if it is a first order filter, the internal capacitance and resistance are changed. If it is a second order filter, that means more number of if it is a first order filter, only a single resistance and a single capacitance are connected, and if it is a second order filter, we use more resistances and capacitance increasing with respect to order of the filter. So we have discussed about the Butterworth filter is having a flat response because the most of the filters are generally allows only a constant proportion of the frequency components. That means this makes the Butterworth filter response a quite flat response characteristics. That means what does a Butterworth filter do means it will eliminate the ripples. All the ripple content is eliminated. Only the flat response is passed through the filter. Okay. So in Butterworth filter, if the order of the filter increases, the flat frequency responses increases with respect to pass band and stop band. That means if we increase the order of the filter, we can get only that response of the flat, won't we get the pass band response, that is the flat response, and the entire ripples are comes under stop band response. So if the denominator of the polynomial, this is the how we can define the Butterworth filter. How can we define the Butterworth filter means, if we see the denominator of the polynomial of the transfer function. So after analyzing the Butterworth filter, particular Butterworth filter, it is a low pass filter or a high pass filter, or it is a first order filter or a second order filter. If we analyze the particular transfer function, in that specific transfer function, if we have the denominator as a Butterworth polynomial, that means we have to identify the transfer function denominator. If the denominator of the transfer function is having the Butterworth polynomial, so that particular transfer function is identified with respect to a Butterworth filter. So how to state or how to specify this constraint means, so how can we identify the given filter transfer function with respect to Butterworth filter means, the Butterworth filter transfer function is always consisting of a Butterworth polynomial. We can identify the Butterworth filter transfer function through a specific range of polynomial, through the specific range of polynomials. So these are the polynomials which we discussed in the previous class, depending upon the order specification. Depending upon the order specification, if it is a first order filter, so s plus 1 is the polynomial. If it is a second order filter, s square plus root 2 s plus 1 is the second order of the Butterworth polynomial. So this is a third order of the Butterworth polynomial, and this is a fourth order of the Butterworth polynomial, fifth order, sixth order. So this condition and enter this type of discussion will go on. So if we identify the Butterworth polynomial with respect to the transfer function of a specific filter, and that type of filter is called, or that type of filter is defined with respect to a Butterworth filter. So if we go into the in-depth discussion of coefficients, if we see the coefficients of the Butterworth filter, if we define the coefficient point of view of the Butterworth filter, see here is the first order of the Butterworth filter coefficient is having 1. That means the lowest order of the Butterworth filter. If we observe whatever the degree or whatever order, either it is a first order or First order is the lowest order of the Butterworth filter, and eighth order is the highest order. So if we observe whatever the order or whatever the degree from A1 to 8, or from the order from 1 to 8, so whatever the degree or whatever the order, the highest polynomial, all higher order coefficients have the order 1, and the lower order coefficients have the order 1. See here, all the higher order coefficients are having the order 1 here, and again same coefficients are having the order 1 here. That means this makes here, whatever it may be the degree or whatever it may be the order, highest order polynomial, all higher order coefficients will have order 1, and all the lower order coefficients will have the order 1. So this is about the coefficient specification with respect to Butterworth polynomial structure. So this almost we discussed in our previous classes. And another thing which we are going to revisit is the properties of Butterworth filter. So it may be the second order, or it may be the nth order filter. So what is the Butterworth filter stating here means, so whatever it may be the order of the coefficient, whatever it may be the order of the coefficient, see here. So if the coefficient of highest order is s is always 1, and which is always lies with respect to the order, that means what is the first point of the property stating? It may be the second order, or it may be the third order. So if we see the highest order filter, that means if we say second order, and if we take the fifth order, and if we take the eighth order, see here, in the particular order specification, if we see here, second order, fifth order, and eighth order, if we see the coefficients of second order, fifth order, and eighth order, so it may be the second order or fifth order or eighth order, the highest coefficient of s is always 1. See, the highest coefficient of s is always 1. And also see the coefficients of the order specification, second order, fifth order, and eighth order. It may be the second order or fifth order or eighth order coefficients of the S component is always 1 for any order filter. So whatever it may be the order of the filter, the initial coefficient and final coefficient is always 1. Initial coefficient and as well as the final coefficient is always 1. That makes the term as unity coefficients. Okay, either it is a first order or eighth order. Initial coefficient is 1 and final coefficient is 1. That makes the entire coefficient of Butterworth filter as unity coefficient. So if we see the odd polynomials, see here the odd polynomials, third, first and fifth, first order, third order, and fifth order, and seventh order odd polynomials, all these are having the terms s plus 1. See here, in the Butterworth filter order, in the first order, in the first order coefficient, in the third order coefficient, and in the seventh order coefficient, and in the fifth order coefficient. So if we see the Butterworth filter order coefficient, we are always having the coefficient of s plus 1. S plus 1. That means for all the odd terms of the polynomials, s plus 1 is very common. And all for the odd order filters, the remaining are in quadratic in nature. See, remaining the first, except for the first order, the third order, for the third order, and for the fifth order, and for the seventh order, the initial term of the polynomial is s plus 1, and the remaining term of the polynomial is about having a quadrant in nature. So if we see the even order terms, for the even order terms like 2, 4, 6, and 8, if we see the even order terms, all are quadratic in nature only. Most of the terms are quadratic in nature only. We can get two similar poles, either it may be positive, two similar poles, either it may be 2 or positive, or more 2 or negative. Most of the things here we represented the positive polynomials. That means here all the factors are poles in the quadratic in nature. For even order terms, we are having quadratic nature. That means all the poles can be present in the left half of this plane, or having the unity circle, or in the order in, or we are having a particular quadratic nature. That means whatever we can see here in the order terminology or with respect to the coefficient terminology, either it is a first, either it is an odd order Butterworth polynomial or it may be an even order Butterworth polynomial, we can clearly identify a similarity in the term. Similarity in the sense, see here, if it is an odd order Butterworth polynomial, we are having a term of coefficient s plus 1. After the term of s plus 1, we are having a quadratic expression. If we see the even order, that means second order, fourth order, sixth order and eighth order, initial term is represented with respect to a quadratic polynomial, and later we represented with respect to an additional polynomial. That means either we can see a first order, either we can see an odd order Butterworth polynomial or even order Butterworth polynomial. They are having a sequence of coefficients. They are following a sequence of coefficients. So this entire thing of Butterworth polynomial description with respect to the transfer function analysis can be clearly analyzed here in the properties which we discussed in the yesterday's class. These are the properties which we analyzed in the yesterday's class. Now we will discuss it again. So in this discussion of today's class, we will see about the first order Butterworth low pass filter. See here, in this particular first order Butterworth low pass filter, if we see here in this figure, the circuit is quite similar to non-inverting type operational amplifier. The circuit is quite similar to non-inverting type operational amplifier. The circuit is quite similar here with respect to non-inverting type operational amplifier. So this type of classification we discussed in our third chapter, application of operational amplifiers, sorry, linear operational application of linear and non-linear applications of operational amplifiers we discussed there. We analyzed about inverting type operational amplifier, non-inverting type operational amplifiers. We discussed about summing inverting circuits, summing type non-inverting circuits, differentiators, difference operational amplifiers, multipliers and all. So similarly, we are applying that knowledge of application of operational amplifier, linear application of operational amplifier here, okay, in the designing of Butterworth low pass filter. See here, so this is our operational amplifier, 5-terminal device. Two are in input terminals. One is inverting, negative terminal is nothing but inverting terminal. Try to recall the knowledge there we discussed there. So operational amplifier we have discussed before. Operational amplifier is having 5 terminals. Two are input terminals. One is negative terminal is inverting terminal, and positive terminal is non-inverting terminal. And plus VCC and minus VE are DC biasing voltage terminals. Okay, and this is nothing but output voltage terminal. That means operational amplifier is a peculiar structure. It is having 5 input terminals. Two are input terminals and two are biasing terminals, and one is output voltage terminal. So with this particular knowledge of our prerequisite of operational amplifier, we are designing a first order Butterworth low pass filter. First order Butterworth low pass filter. So here we are analyzing a non-inverting type operational amplifier. Non-inverting type operational amplifier in the sense input voltage is connected to the non-inverting terminal. Positive terminal is called as non-inverting terminal. Negative terminal is called as an inverting terminal. So here we have given the input voltage to the positive terminal of the operational amplifier. That's why it is called as an non-inverting type input voltage. And if we give the input voltage to the non-inverting terminal of the operational amplifier, the entire design will be called as non-inverting type operational amplifier. So this is a non-inverting type operational amplifier. See here, the input terminal is connected to the positive terminal of the operational amplifier, and active and the passive elements, resistance, a variable resistance and a capacitance is connected with respect to the input terminal. Okay, and a resistance is connected with respect to the negative terminal and it is grounded, and a negative feedback is connected in order to regulate the gain. Negative feedback always, with respect to our previous knowledge, negative feedback will limit the gain, positive feedback will add the gain. So the negative feedback is connected to the negative terminal of the operational amplifier with respect to output. So and here V0 is nothing but the output terminal. Okay, so this is our circuit description. Okay, so and again we already discussed in the introduction of our filter concepts. So there are certain drawbacks if we design the filter with an complete passive elements, because the loss coefficients will be high, and loading components are high. So if we make a filter with the combination of active elements and passive elements, active elements in the sense operational amplifiers, FETs, transistors, this all falls under the classification of active elements. Passive elements in the sense resistance, capacitance and inductors comes under passive elements. So here what we are doing is, in the designing of first order Butterworth low pass filter, we are combining passive elements like resistance and capacitance, which is connected to the input terminal of the non-inverting type operational amplifier, and we are designing the low pass filter in a combination of active elements with respect to passive elements. So if we see this particular circuit, it is similar to non-inverting type operational amplifier. Input voltage is, I am again restating again, listen very carefully. Input voltage is applied to the non-inverting terminal, which is filtered with respect to this particular RC passive element. That means input voltage which is applied to the non-inverting terminal is filtered with respect to the RC passive element structure. That means the remaining elements are all are active elements. That means active circuit is combined with respect to passive circuit. Depending upon the elements we have used additionally, that means which reflects the order of the filter. That means this RC elements which reflects the order of the circuit at the input terminal of our first order Butterworth low pass filter. we are we are adding an RC poles. We are using only single RC pole pair. That's why it is an lower order. That's why we are designing an first order Butterworth low pass filter. If we use an additional capacitance or additional resistance, thus that makes the Butterworth filter low pass filter as second order. That means we have used a single capacitor here, that makes the first order filter. Here in the first order filter, we are using only a single energy storage element. Okay, so entire in this is the design of first order Butterworth low pass filter. So if we go to the analysis, in the analysis is entire analysis is about transfer function response. Transfer function, important thing is transfer function calculation. So how to calculate the transfer function means, in order to calculate the transfer function, first we have to calculate the gain. Gain calculation is very very important in analyzing the Butterworth filter first order in analyzing a Butterworth filter. So how to calculate the gain means, already we stated here, this is a non-inverting type operational amplifier. In order to analyze the non-inverting type operational amplifier, previously we have calculated the gains for inverting type operational amplifier, for a non-inverting type operational amplifier, for summing type operational amplifier, for integrator, for differentiator, for difference operational amplifier, for all other mathematical operations and all other individual classifications of operational amplifier, we calculated the gain. So I am restating that gain here in the equation 1. The non-inverting type operational amplifier, the input voltage is connected to the positive terminal of the operational amplifier. That's why the gain A naught is equal to, okay, how to state the gain. Gain is nothing but a ratio of output voltage with respect to input voltage. Okay, input voltage here we represented with respect to V suffix A, voltage of the total gain function. Okay, so that is stated with respect to 1 plus Rf. Rf is nothing but feedback resistance. See here, Rf is nothing but feedback resistance, and R1 is nothing but input resistance. Okay, and V naught is equal to, okay, with this equation 1. So if we rewrite that equation 1, V naught is equal to A naught into V suffix A. So from the circuit, from this particular circuit of the non-inverting type operational amplifier, if we apply the gain to the specific function, Okay, what will be the gain value? Gain value V suffix A is equal to, okay, V input into volt after applying the voltage division rule in the above circuit. In this particular circuit, if we apply the voltage division rule, so what will be the value of voltage across the terminal VA suffix A is equal to input voltage into voltage stored across the capacitor 1 by j omega c, and the behavior of resistor and capacitor. Resistor is having input resistance R ohms plus 1 by j omega c. Okay, so if we substitute this equation in above terminal, that is V naught in equation 2, that is V naught is equal to A naught into V suffix A. So V suffix A is equal to V suffix A is equal to V input into 1 plus 1 by 1 plus j omega into j omega c into R. So if we substitute this entire expression of V suffix A in equation 2, this will be the V naught. V naught is equal to A naught into V input divided by 1 plus j omega 1 plus j omega c into R. Okay, so after stating the individual terms of output voltage is stated with respect to gain A naught, and input voltage is represented with respect to 1 plus j into 2 pi f, where omega is represented with respect to 2 pi f. Here, see, here we are having 1 by 1 plus j omega c into R, where omega is stated as 2 pi f. After representing that omega as 2 pi f, here this is the final expression. That means the gain value is represented with respect to output voltage with respect to the input voltage, that is equal to A naught divided by 1 plus j into 2 pi f c into R, that is equal to A naught divided by 1 plus j into frequency with respect to higher order frequency. Okay, f suffix h is nothing but higher order frequency or higher cutoff frequency, that is represented with respect to 1 by 2 pi rc. Okay, where A naught is nothing but pass band region, and magnitude of this entire term, if we take the magnitude of this entire term, that is represented with respect to this. Okay, and this is nothing but phase margin. Okay, this is nothing but magnitude and this is nothing but phase difference. So if we take the frequency response for granted, so see here, so this is the frequency response plot. So if we analyze the up to now, what we discussed means, up to now we discussed about the behavior of transfer function. Up to now we discussed about the behavior of transfer function. So after we discussing the behavior of transfer function, if we plot the frequency response curve and if we analyze the frequency response curve, okay, frequency response curve, so on the x-axis we have gain margin, on on y-axis we have gain margin, which is represented in decibel. On x-axis we have frequency. So if we analyze the frequency response curve here, the frequency response curve is analyzed in three aspects. See, entire frequency response curve is analyzed in three aspects, where the frequency is very small. That means if the frequency is very small, applied frequency is very small, the higher cutoff frequency, then the magnitude of the transfer function output with respect to input, that is equal to the gain margin A naught. That means the voltage gain remains constant for this type of lower frequencies. Okay, if the frequency f is equal to fh, if the frequency f is equal to fh, if we take the magnitude of the transfer function, okay, that is equal to A naught divided by root 2. That means here the frequency is equal to the higher order frequency, the gain value is almost equal to the low pass filter. The magnitude value at f is equal to fh, the magnitude value is just decreased with a small magnitude around up to 0.707. So see here, you can clearly see in the response characteristic at this is the f suffix s cutoff frequency, and this is below cutoff frequency, and this is above cutoff frequency. Below cutoff frequency region is constant. See here, this region is having a constant structure. At cutoff frequency, it is just at cutoff frequency here, it is just decreased by a small quantity of 3 decibel. 3 decibel. If we the frequency is further increased, the gain value is decreased up to, the gain value is again decreased. See the behavior of gain. See the behavior of gain. If we increase the frequency beyond the higher order frequency or upper cutoff frequency, the gain margin is decreased up to minus 20 decibel per by 20 decibel per decimal. Okay, that means if we further increase the frequency, the response characteristic is decreasing. The response characteristic is decreasing. That means the entire behavior of the frequency response characteristic is stated under three cases, where the first case is represented with respect to the frequencies very less than the frequency is very less than the higher order frequency, and the second case where the frequency is equal to the cutoff frequency, and third frequency where the frequency is greater than upper cutoff frequency. So at what particular condition our Butterworth first order Butterworth low pass filter will transmit the signal, means up to this particular constant magnitude. See, I am highlighting up to this particular constant magnitude only the Butterworth filter, low pass Butterworth first order Butterworth low pass filter will transmit this particular region only, and this entire thing will be represented as stop band. This entire thing, only the constant characteristic, this particular constant characteristic will be stated or passed through the first order Butterworth low pass filter. Okay, only this region, only this constant region is identified as pass band region, and remaining region, this rippled region, is identified as stop band region. Stop band region. Okay, is it clear? Is it clear? So in today's class, we discussed about Butterworth first order Butterworth low pass filter. We analyzed about the design of non-inverting type operational amplifier design. Okay, and the usage of a single RC pole pair makes the filter as first order filter. If we use an additional pole pair, RC pole pair, that makes the second order filter by design. Okay, and next we discussed about the transfer function, and next we analyzed the phase margin magnitude, and we analyzed the phase margin, and next we discussed about the three different cases, and we analyzed the frequency response characteristics, and next we revised and restated the various properties of Butterworth polynomials, and next we have seen the odd order coefficients of Butterworth polynomial and even order coefficients of Butterworth polynomial. Next we discussed about various characteristics of flat response characteristics of Butterworth polynomials. So this is about the today's class discussion. We are discussing about the design and analysis of Butterworth active filters, and in today's class we analyzed about first order Butterworth filter. Okay, we restated about the basics of basics like definition of filter. Okay, filter is a reactive circuit which passes and allows a specific band of frequencies, and it can also reject or it can also stop the frequencies other band of frequencies, where mostly a filter is nothing but a frequency selective device. We restated the definition, and we also discussed about the definition of pass band. Only the filter is having a specification of passing the frequency component. We also stated about stop band, a range of frequencies where filter can reject the frequency components, and next we discussed about various applications of filters, and next we discussed about various classifications of filters. Next we stated about how to design and active filters and passive filters, and what are the advantages of combining active elements and passive elements, and next we discussed about various advantages of active filters over passive filters, Next we explained about disadvantages of active filters. Next we stated various types of low pass filters, high pass filters, band pass filters and all pass filters. And next we explained about the magnitude of transfer function, and next we stated about order of the filters. And next we discussed about the introduction to the Butterworth approximation. And next we stated the order as well as the coefficient of the Butterworth filters. And next we discussed the first order, and next we discussed about the first order Butterworth low pass filter, okay, which falls under the classification of low pass filter of initial order, that is first order. We analyzed the first order Butterworth low pass filter with a classification of non-inverting type operational amplifier. Why it is non-inverting type operational amplifier means the input supply is connected to the non-inverting terminal, positive terminal of the operational amplifier. It is a first order Butterworth filter because we are having a single RC pole pair. We analyzed we designed the Butterworth filter with the help of operational amplifier. We analyzed the transfer function and we explained the frequency response.